Hello friends, in the previous video we have seen some basics regarding the strength of material. Now based on that we are going to see some problems. We are not just going to solve the problems but understand the mechanics behind it. Now let's see the first problem. Now it says that find the minimum diameter of a steel wire which is used to raise a load of 4000 Newton if the stress in the rod is not to exceed 95 megapascal. That means it says that a steel wire is used to lift a weight of 4000 newton, and because of that the stress at any point throughout this wire should not exceed 95 megapascal. Now let me tell you that in every design is dependent on two things. One is strength and the second one is stiffness. What is the meaning of this? So let's see about strength. That means they set a limit of stress. That means if let's say it has sigma cap. If the stress in any material exceeds beyond this sigma cap, then we say that the material is failed. For example, the mild steel. If we take mild steel and if we see the stress strain diagram of mild steel, we get something like this, correct? So this is the yield point at this point, sigma yield. Now we have taken this yield point sigma y as sigma cap, that is the limit of stress. If the stress in mild steel goes beyond this value sigma y, then we say that the material has failed. And so this is the design criteria of strength. This is how sigma cap is selected. And stiffness, suppose if we say that here the limit is set by delta L. If during the operation the deformation exceeds the deformation exceeds this delta L, then we say that the material is failed. If the deformation is less than the limit set by the designer, then we say it as safe. So this sigma cap they have given as 95 megapascal. We need to ensure that key stress should not exceed this. So this is how the diameter of this rod has to be calculated. Now based on this condition we know that stress is nothing but load upon area. It should be less than that of 95 megapascal. So megapascal I can write it as Newton per millimeter square. So load given is 4000 upon area is pi by 4 d square. Why I am taking pi by 4 d square? Because they have mentioned here steel wire, that means it is circular in cross section, and by solving this we will get the diameter should be greater than or equals to 7.32 mm. 7.32 mm. That means if the diameter is greater than 7.32 mm, that means our element is safe. Correct? Now we move on to the next problem. What it says is find the Young's modulus of a brass rod of diameter 25 mm. They have given a brass rod which is of 25 mm diameter. 25 mm, which is subjected to a tensile load of 50 kilonewton. Okay, 50 kilonewton. Again, what he is saying is when the extension of the rod is equal to zero point 0.3 mm. Now, because of 50 kilonewton acting on this element, the extension of the rod, that means delta L is saying is zero point 0.3 mm. Now he is asking me to find Young's modulus. We know that stress is directly proportional to strain, so stress is equals to modulus of velocity into strain. Now we have to find this Young's modulus. So Young's modulus is given by stress upon strain. So how to find stress? We know that stress is nothing but load upon area. How much load is given over here? 50 kilonewton. So I'll write it 50 into 10 raised to 3, and area, a rod of diameter 25 mm. That means I can find out pi by 4 into d square, 25 square. So its unit will be megapascal because Newton per mm square. So the stress that I'm going to get here is, for calculating here, I'll get stress as 101.86 megapascal. Now I have got this stress. Now what about strain? Strain, I know that strain is nothing but change in length upon original length. What is the extension of the rod? Extension of the rod is 0.3 mm. And what is the length of the rod? The length of the rod given here is, earlier original length is 250 mm. 250 mm. So my writing here is what we will get strain value as 0.0012. Now we have got the stress value and the strain value. Just substitute it, in this. What we will get here is, if we just substitute it, then we get the Young's modulus as 101.86 upon 0.0012. So then we get the strain value, modulus of velocity as 84 84.883 into 10 raised to 9 Newton per Newton per meter square. So I can write it as 84.883 gigapascal. Now let's move on to next. Now this is the problem of a stepped bar. Now before solving this problem, now these are the diameters given over here: 20, 30 and 50. Three sections, three steps, 1, 2 and 3, and on the three sections 35 kilonewton of load is acting tensile, and the lengths are given over here: L1, L2 and L3. All the dimensions are in mm. So before solving this problem, I would like to tell you about how to find the load at any section for a stepped bar. In case of a stepped bar, suppose a stepped bar is like this, and some load is acting over here is 25 kilonewton, and here suppose in this direction is 40 kilonewton, and here it is 15 kilonewton. 15 kilonewton. The sign conventions we can use for this as, if it is pulling the element then it is plus, if it is compressing the element then it is minus. So by doing that, suppose I want to find the load at this section. So what I have to do is just find the algebraic sum of all the forces transmitted to that section from either side. Suppose that means I have to calculate the stress at this section, correct? So on either side, what is the sum of forces on this side? What is the sum of forces on this side? It is nothing but 25 megapascal, and it is tensile, so plus 25. We can cross check that from left right hand side it comes as plus 40 minus 15, it has plus 25. Yeah, it is same. That means if you have to find the load at any section, what you do is just do the algebraic sum from either side. Now here I find that left side is very easy because there is only one load, so I'll directly write it as 25. Suppose I need to find, I'll draw it again. At this section, suppose at this section I need to find out again. If we look at either side, here it is 25. If we look at either side, here there are two loads, 25 and 40, and here there is only 150. So I can go from the right hand side and directly say that the load at this section x11 is directly minus 15. So this is the simple technique that we should use for finding the load at any section. It is nothing but the algebraic sum of all the forces transmitted up to that section from either side. Whichever side you feel easier, uh, you go from that side up to that section. Now we will move on to our problem. What it says that, okay, now here we need to find the stress. We need to find the stress in first section, in second section, as well as third section, and the total extension of the bar. Total extension of the bar. So here we can find it out like this. Now here, to find the stress in first section, if I draw a section XX, what is the load on this section from either side? We can check that from either side there is only one load, that is 35 kilonewton. So from first, and the load on this is P1. I can say that 35 kilonewton. The same thing on second section. What is the load on either side? It is only one and the same load, so again 35 kilonewton, and same for third, it is 35 kilonewton again. It's it's only the matter of area and diameter which will result in changing in different stresses in all the three sections. Sigma 1 is nothing but P1 by A1. We know that P1 is 35 kilonewton upon area is pi by 4 into d1 square, that is 20 square, and you will get the stress in the first section. Now the second one, the stress in this section you will get is 111.408 megapascal. Again the stress, similarly calculate P2 by A2. So it will be again 35 kilonewton, just the diameter will change, pi by 4 into the diameter. I think it is, what is the diameter here is 30 and 50. Okay, 30 and 50. So 30 square, you will get something, we'll get here as 49.51 megapascal. And similarly find sigma 3, just only we need to change the area diameter over here, and it will be 17.825. We can see that as the diameter goes on increasing, the stress in each element in each section goes on reducing. Now they have also asked us to find the total extension. We know two formulas for for extension, that is, what are those two formulas? They are delta L is equals to PL by AE, as well as integration of P dx by AE. Now we use this formula when P, A and E are constant, and we use this when any one of these three varies. So look at this. Here for section 1, here section 1 the load is constant throughout this, the diameter is constant, and it is made up of same material, so E is also constant. So that means we can say that delta L total is nothing but delta L of 1 plus delta L of 2 plus delta L of 3. So delta L of 1 is P1 L1 by A1 E1. Now here and here it will be P2 L2 by A2 E2, and again P3 L3 by A3 E3. Now here, as P1 equals to P2 equals to P3, and all the three sections are made up of same material, that's why E1 is equals to E2 equals to E3. So we can take out P by E common, and area is pi by 4 d square, so that means 4 by pi we can take common, and we can write here as L1 upon d1 square plus L2 upon d2 square plus L3 upon d3 square. So we know that P is 35 kilonewton and E is given as 2.1 into 10 raised to 5 megapascal multiply by 4 by pi. L1 is 200 d1 square, that means 20 square plus. Now you need to remember that if on any section the load is compressive, then instead of plus it will come minus. We already have seen the sign conventions. That means if the loads are pulling the element, then we use plus because the length will increase, and if the load, here we have seen, if the load are pulling, if the load is pulling the element, then it is plus. If the load is compressing the element, then it is minus. So here in each section the load is pulling the element, that's why we are using plus. Now here second length is 250 upon 30 square, again 220 upon 50 square. By solving this, what we will get is, we'll get as 0.183 mm. This is the total deflection of the bar. Now we have solved these three problems. I would like to give you a one bonus question, and I hope that you will get the correct answer, and please let me know the answers. What do you think in the comments below? Now this is a simple question. There is one element and this element is made up of two materials, which is E2 and E1. This is first element, and this whole element is made up of two different materials. Now let's say this as 1 and this as 2, and as they are of two materials, so they have different values of Young's modulus, and load P is acting like this. Then what is the value of stress? I'll give you options. First option is P by A, second option is P by A into E1 upon E2, third option is P by A into E2 by E1, and fourth option is P by A into E1 minus E2 divided by E1 plus E2. E2 and also it is given that E1 is greater than E2. E1 is greater than E2, and also tell me that whether if delta L1 is the deformation of first section and delta L2 is deformation of the second section, then which deformation is greater than the other, or else both are same. If delta L1 is greater than delta L2, or delta L2 is greater than delta L1, or both are same. So three options, and that means here you have to tell about the stress in both the sections, and here you have to tell about which deformation will be greater. So please do write the answers in comment, and we will discuss about this question in our next video. So thank you very much.